Suggesting that water is the most unusual liquid on Earth might sound like saying bread is the most unusual food. After all, it feels so familiar and abundant to us. But water remains one of the most mysterious compounds on this planet, characterized by a large number of anomalies, continually defying the ordinary and refusing to conform to the rules that govern most substances. Water is a paradox, a seemingly gentle substance, but capable of wielding enormous power. Turbulent and restless by nature, unrelenting, capable of carving through mountains and reshaping entire coastlines, quietly transforming our world. And yet, in its presence, we are able to find profound calm. The quiet reflections are inviting us to pause, to breathe, and to let go of the restless motion of our thoughts, the stillness drawing us into its serene. Its calm invites our own, as if, for a moment, we are in sync with its tranquility. Water speaks to something deep within us, drawing us to its presence in ways we cannot always explain. And yet, even in its stillness, water is never truly motionless, only waiting, ready to ripple, to shift, to flow onward once more. It's the ultimate force of change, remaining in a constant state of flux. Its chaotic motion defies prediction, many of its deepest mysteries and fundamental questions still remaining unsolved to this day. So to think of it as simply ordinary would be to overlook one of the strangest substances on this planet. To truly appreciate water's weirdness, first we need to understand its blueprint, the phase diagram. Because right here, at the fundamental level of how phases interact, water is already breaking the rules. On the horizontal axis, we have temperature in degrees Celsius. And on the vertical axis, we have pressure, typically shown in pascals or atmospheres. The diagram is then divided into 3 regions, each representing a different phase: solid, liquid, and gas. These curved lines are also known as phase boundaries, lines that represent the conditions where 2 phases can coexist in equilibrium. If we draw a line across these boundaries at the ambient atmospheric pressure, or 1 atmospheric, we will find 2 points that we are all very familiar with: thermal equilibrium at 0 degrees and the boiling point at 100. Tracing down the phase boundary, we can see that the boiling point gets lower as the pressure decreases, meaning at high altitudes, you can boil water at lower temperatures and enjoy a freshly brewed tea that won't burn your mouth. Following down the axis, we will eventually reach a point where all 3 phase boundaries meet. This is the triple point, the only set of conditions where ice, liquid water, and vapor can all exist together in perfect balance. Below this point, liquid water is no longer stable and transitions directly between solid and gas. An example of these extreme low pressures can be found on Mars, where water cannot exist as a liquid. Under its thin atmosphere, liquid would boil away almost instantly, and the rapid heat loss would cause the rest to freeze into ice. A similar experiment can be carried out right here on Earth by throwing boiling water into the air on a bitterly cold day. The hot droplets are already carrying a lot of thermal energy, and once dispersed into freezing dry air, that heat is lost almost instantly. Some water molecules escape directly as vapor, while the remainder cools so fast the droplets solidify into ice crystals. So just like on Mars, the water is being pushed across the phase diagram into regions where liquid isn't stable. Moving up the boundary from the triple point, we can see the line between liquid and gas eventually comes to an end, a point beyond which the line simply disappears. This is known as the critical point. Beyond these conditions, water becomes something entirely different, with no distinction between a gas-like and liquid-like state, also known as a supercritical fluid. When this state of water is put to use, engineers refer to it as supercritical steam, which is far denser and more energetic than ordinary steam. capable of carrying heat with remarkable efficiency. It flows like a gas, but transfers energy like a liquid. That's what makes it so valuable for generating electricity in advanced power systems. The behavior of water along the liquid-gas phase boundary is not unusual. The steadily rising curve with increased pressure up to the critical point is in fact almost a universal feature shared by nearly all liquids. But where water starts to break the rules is here, along the solid-liquid boundary. For most substances, increasing pressure makes the solid phase more stable. Out of more than 200 million known substances on our planet, water is one of only a handful that behave the opposite way. Iron, for example, behaves just as we'd expect. Deep inside Earth's core, where pressures reach millions of atmospheres, iron remains solid even at temperatures over 5,000 degrees Celsius. But farther out at lower pressures, that same iron begins to melt, forming the liquid outer core that drives Earth's magnetic field. In other words, for almost every substance on the planet, squeezing harder raises the melting point, with water being one of the rare exceptions. The fact that the solid-liquid phase boundary slopes towards the left might seem insignificant, but its effects ripple through everything from everyday life to the planet itself. It's one of the reasons a skate blade glides so effortlessly across ice. Although it is not the pressure from the blade alone, ice is coated by a thin liquid-like surface layer, and the moving blade can generate additional meltwater through friction. Together they create the microscopic lubrication that makes skating possible. It also helps explain glacier motion. Deep beneath a glacier, immense pressure can bring the basal ice close to melting, and the water that forms there can help the glacier slide over the ground below. Perhaps the main reason we think of water as ordinary is because it's everywhere. We drink it, swim in it, and watch it fall from the sky. Nearly every liquid we encounter on a daily basis is largely made up of water. And perhaps that's why its strangeness hides in plain sight. Although there are a few substances that share some of its anomalies, water is the only substance on Earth found naturally in all of its three phases, forever cycling between them, quietly shaping our world. And while the phase diagram shows how water behaves, to understand why, we have to look closer, beneath the curves and boundaries, into the invisible network of bonds that make the liquid world possible. In our first chapter, we learned the basic building blocks of the water molecule, the classic bent shape of H2O. But it is only when looking at the molecule in 3 dimensions when we start to understand the molecular geometry a little better. If we rotate the molecule, 2 features that are often overlooked in basic drawings start to emerge. The oxygen's lone pairs. They're not atoms, but regions of negative charge, invisible in the real world, yet powerful enough to shape the entire geometry. Now we can start to notice the shape of the molecule. The 2 hydrogens and the 2 lone pairs sit at the 4 corners of a tetrahedron. In perfect symmetry, these corners would lie 109.5 degrees apart. But water doesn't reach mathematical perfection. Due to the repulsion from the lone pairs, the hydrogens are pushed inward and narrowing the angle to about 104.5 degrees. This echoes a larger underlying principle in nature. Nothing is ever mathematically perfect. Even the shapes we treat as symbols of symmetry, the crystal arms of a snowflake, the hexagons of a honeycomb, even the straight line of a distant horizon, are only approximate perfection. To the naked eye, these shapes may seem perfect. But look closer, and each one warps under external and molecular forces. Tiny imperfections built into their very geometry. And the water molecule is no exception. If we look at the nature of the covalent bonds between the atoms, we start to understand why. Each covalent bond is astonishingly small, existing in a region of space of approximately 0.096 nanometers long. And the best way to describe the nature of this bond would be to imagine a tiny spring. This imaginary spring exists in a quantum mechanical electron cloud, vibrating in quantized modes up to about 113 trillion times per second. The vibratory movement means the hydrogen atoms swing in and out by a few degrees, constantly widening and narrowing the bond angle of the molecule. As the temperature rises, the vibrations intensify and slow down as it cools down, but they never stop. In other words, the bond angle of 104.5 degrees is never exactly the same from one moment to the next. This restless motion is the essence of liquid water at the smallest molecular level, which then raises a deeper question. If liquid water is so restless by nature, can it have a structure? And where does that structure come from? Answering this question would require tracking every single water molecule in real time. But water reorganizes itself trillions of times per second. We simply do not have the technology to do this. Instead, scientists have built the picture statistically by taking millions of microscopic snapshots. And from that blur of motion, something remarkable emerges. A liquid structure isn't fixed in space. It's revealed only in time. To reveal this shape, we first need to look at how the water molecules interact with each other. The oxygen's lone pairs occupy regions of concentrated negative charge. These areas act as natural docking points for the positively charged hydrogens of neighboring molecules. The result is that every water molecule prefers to form up to 4 hydrogen bonds, 2 donated from its hydrogens, and 2 received through its lone pairs. A single hydrogen bond survives for only about 1 picosecond, or a trillionth of a second. And as these bonds form and break, a familiar pattern emerges. Their preferred directions line up with the 4 corners of a tetrahedron, echoing the shape of the molecule itself. This tetrahedral cluster, one central molecule surrounded by 4 neighbors, is the arrangement water prefers. It's the configuration that hydrogen bonds most strongly favor, the one they continually attempt to rebuild. But in reality, this perfect cluster is only a snapshot in time. Although each water molecule naturally aims for 4 hydrogen-bonded neighbors, thermal motion constantly disrupts that balance. Some molecules only bond with 3 neighbors, and some bond with 5, depending on how the network shifts around them. And in rare moments, a single hydrogen connects between 2 different oxygens at once, forming a bifurcated bond. It's a split connection, weaker and far less stable than a normal hydrogen bond, lasting only for a fraction of a picosecond before the network rearranges again. These irregularities are not flaws. They are what gives liquid water its dynamic nature and its remarkable, ever-shifting character and restless personality. Perhaps then, the best way to think of water's structure is to imagine shaking a box full of weak magnets, connections forming and breaking in an endless shuffle. Organized chaos, as once described by an Irish biophysicist, J.D. Bernal. And all that motion matters. Every moment a hydrogen bond flickers, a tiny pulse of energy is redistributed through the liquid. Even in a small droplet, trillions of these pulses ignite each second, gathering and carrying heat with a quiet power unique to water. Every living thing on our planet depends on one quiet anomaly of water: its extraordinary heat capacity. Without this single property, Earth's climate, the oceans, and even our own bodies would swing wildly in temperature, and life as we know it simply couldn't exist. Only a few cubic meters of ocean water can hold as much heat as the entire atmosphere above it. And when you consider that the average depth of the world's oceans is nearly 4 kilometers, it becomes clear just how important our oceans are for the planet's climate. But what exactly does heat capacity mean? At its core, it's a very simple concept. It measures how much energy a substance has to absorb to warm up. Water has a specific heat capacity of 4.184 joules per gram degree Celsius, meaning it takes 4.184 joules of energy to heat 1 gram of water by 1 degree Celsius. To understand just how resistant water is to heating, we can compare it to the amount of energy we burn when running. During a 1-hour run, our body releases roughly 800 kilocalories of energy. That's enough energy to warm about 800 liters of water by 1 degree, roughly the volume of 4 full bathtubs, which may sound impressive until we compare it with a real body of water. For a lake the size of Loch Ness in Scotland, we would have to keep running for roughly 10 billion hours, or about 1.4 million years, to raise the temperature by just 1 degree. And even if every single person on Earth, all 8 billion of us, started running flat out, it would take 12,000 years of collective non-stop running to see a tiny temperature difference in the Pacific Ocean. To heat water simply means adding energy to it, to set its molecules trembling with ever greater motion. And the vast majority of that energy, across Earth's history, has come from a single source, from the great engine of our planet, the sun. Every day, as the sun climbs over the horizon, marks the start of a colossal transfer of heat. Some of it warms the air, some stirs the winds, but much of it plunges straight into the water that's covering 70% of our world. And when all that solar energy enters water, something extraordinary happens. Water warms reluctantly. To understand why, we must once again look to the hydrogen bond network behind so many of its other remarkable characteristics. As we have learned, a single hydrogen bond forms when the positively charged hydrogen of one molecule is attracted to the lone pair regions of a neighboring oxygen, the area where negative charge is concentrated. By chemical standards, hydrogen bonds are weak, around 20 kilojoules per mole. They are stronger than van der Waals forces, yet far weaker than covalent bonds. Crucially, these bonds are also highly directional. They exist only when two molecules meet at just the right distance and at just the right angle, tilt the angle slightly, or increase the distance by even a fraction of a nanometer, and the bond begins to weaken, stretching and bending, before eventually fading away. This is exactly what happens when thermal energy enters water. The energy doesn't simply snap hydrogen bonds apart. Instead, it increases molecular motion just enough to disrupt their precise alignment, twisting molecules out of position until the attraction simply ceases to exist. Now let's consider the scale of this process. In a single glass of water, there are roughly 8 septillion molecules, already in constant motion, vibrating and rotating, slipping past each other. And because each of these molecules is linked to up to 4 other nearby molecules at any given moment, there are roughly 15 septillion hydrogen bonds in a glass of water. But that is only a frozen snapshot in time. Due to the restless nature of the molecules, each of these bonds rearranges itself roughly 1 trillion times per second. That means about 15 undecillion hydrogen bond rearrangements every second inside a single glass. Now consider how many glasses of water make up an ocean. When scaled across entire ocean basins, spanning kilometers of depth and vast moving currents, the numbers leave the realm of intuition altogether. This is the quiet power of the hydrogen bond. On its own, a single bond is weak, and it only takes a tiny amount of energy to disturb. But woven into an enormous, ever-shifting network, it now requires a colossal amount of energy to raise the average molecular motion, what we experience as temperature. And once that colossal amount of thermal energy is absorbed, it doesn't just simply vanish, it moves with ocean currents around the globe. What begins as sunlight striking tropical oceans, like the Gulf of Mexico, does not stay where it lands. On the Atlantic scale, this becomes the Atlantic Meridional Overturning Circulation. And inside that system sits one of the most famous surface currents on Earth, the Gulf Stream, a fast-moving boundary current flowing from the Gulf of Mexico across the Atlantic, transporting warm surface seawater thousands of kilometers toward higher latitudes. Along this journey, some of this warm water lose heat to the atmosphere, become denser and sink. Then, kilometers below the surface, the colder water flows back south, completing a deep, planet-sized loop. And the flow of this gigantic current is immense. It begins at roughly 32 million cubic meters per second in the Florida Straits, and the broader Gulf Stream circulation can be nearly 5 times larger in the open Atlantic. This means that every second, it drives an extraordinary river of heat towards the North Atlantic, enough that in just a few days, it transports as much thermal energy as humanity gets from burning fossil fuels in an entire year. From the North Atlantic, the prevailing westerlies take over, sweeping the milder, moisture-laden maritime air eastward, softening the climate of the British Isles and Western Europe. This combination is part of why a city like London can experience comparatively mild winters, while parts of Canada at similar latitudes can plunge into far harsher cold. The ocean holds the heat. The atmosphere carries it onward. But the ocean is not the only way water moves energy across the planet. In fact, some of water's most remarkable work begins when the water molecules leave the ocean behind altogether. Which brings us to our next chapter, water in its invisible form, revealing one of its most powerful roles on this planet.